Hello, my name is Anuj. This is a quick overview of the paper Estimation and Applications of Quantiles in Deep Binary Classification. This is what we'll be going through, the motivation behind why we're doing this, the binary quantile regression loss, the various applications that it has, particularly in the regards of uncertainty quantification, how it's used to improve robustness and improving explainability. Then we'll talk about how we can speed it up with something called Lipschitz adaptive learning rates. We'll go over the limitations and how this can be taken forward, and finally I'll give you a one-slide conclusion. So to start, let's look at the motivation behind this. So on the left-hand side here, I have a deep neural network designed for binary classification. Please ignore the fact that the hidden layers are not fully connected, just assume that they are. But you've got an input layer, the hidden layers, and finally an output neuron. This output neuron's output is given by this equation here. P is equal to sigmoid of summation wixi plus p. And this sigmoid of x is nothing but the sigmoid activation function. Now you can actually go a step back and view this as the probability is equal to sigmoid of f of x and call this f of x the latent function. Because after all, when we assign a class label, we just check whether or not this p value is less than or equal to 0.5. We say if p is less than 0.5, it's class value 0, otherwise it's class value 1. You can just apply that to f of x directly and say if f of x is less than or equal to 0, then the class value is 0, otherwise the class value is 1. And really that's what the network is learning here. It's learning this latent function, and sigmoid is just something put on top of that to convert it into a nice probability value. And you train this with the standard binary cross entropy laws that everyone is aware of. Now the thing about this is that sigmoid itself doesn't capture anything about the uncertainty of f of x. It's just telling you how far away f of x is from the threshold value 0. And binary cross entropy again is only able to capture what is effectively the mean of this latent function. You can view it as an equivalent of mean square error from the binary classification world because it's based on maximum likelihood estimation. And this combination as such doesn't capture anything regarding the uncertainty of the latent function. Now you might wonder, why does that matter? So let's take a step back into the regression setting and look at something that's called a quantile. So on the left hand side here, we have this data set with just two variables, acceleration and time. And you can see that they have this particularly interesting relationship between them. And you can see that for the most part in this region, the points are very close together, sort of clustered together. But on the right hand side here, they're actually very spread apart. Now, if you were to model just the mean function or the average function that's being computed here, you would get a line that would go through the points and you get a single curve. There's no way that you would be able to capture the uncertainty of the curve, especially towards the right hand side of this graph. And that's where quantiles come in. So mathematically speaking, the definition of a quantile can be given by this equation on the right, where the probability of f tau of x is greater than f of x is equal to tau. What that really just means is that there's a control parameter we have called tau, and this tau controls what percentage of points lie below the curve and what percentage of points lie above the curve. To put it bluntly, if you take a look at the example on the left hand side here, we have these various colored graphs. The bottom one over here, this red curve corresponding to Q0.1 is the 10% quantile, or tau is equal to 0.1. And what it means is that 10% of the points that are present in this distribution lie underneath this curve, or this curve is greater than 10% of the points that are present. The most common one that you're likely to come across is the median, given by tau is equal to 0.5. And you can view that as the curve that splits the points into two halves. 50% of the points lie below and 50% of the points lie above. And likewise, we have this purple line on top here, which indicates the 90% quantile. So 90% of the points lie below it and only 10% lie above. And you can see here that when we add quantiles into the mix, instead of getting just a single curve, we're actually able to capture the uncertainty of the entire distribution. We gain a lot more information. And this is very common. You see it very often in regression settings. But unfortunately, or until this point at the very least, people really haven't thought about this in the binary classification context. Because if you think about it, if we were able to apply these quantiles to our latent function, we now have a way of capturing the uncertainty present within the latent function itself, which directly translates to the capturing uncertainty in the class labels that we generate. So this is the binary quantile regression loss that we've come up with. So the first line here that you see, y is equal to I z greater than or equal to 0, is exactly what I talked about in the start, where all we're really doing is we're having an indicator function as to see whether or not the latent function is greater than 0 or not. If it's greater than 0, class 1, otherwise class 0. And you can model this as an f of tau of x plus some epsilon e, which is basically like an error term. And this error term comes from what's called the asymmetric Laplace distribution. So if you take a look at the graph that corresponds to this asymmetric Laplace distribution, you can actually see that this is what it looks like. So the blue curve over here is the derivative of sigmoid, and this red curve here is the asymmetric Laplace distribution or density. And as I move this control parameter, it's called P here, please ignore it, it's referred to as tau. I haven't used T because it's been used elsewhere. But as you move the slider, you can see that what it really does is it controls the area under the curve, or what percentage of the curve actually lies to the left-hand side of 0 and what lies to the right-hand side of 0. If you take a look at this graph, which is basically just the probability distribution, which you can just get by integrating that function, you can get a nice comparison between our new distribution function and the sigmoid function. As you move this quantile slider, you can see that all it's sort of controlling is the area under the curve. So for example, add quantile equal to 0.5 here, you can see that it's sort of half and half. Half of the area falls to the left hand side, half of the area falls on the right hand side. And it's very similar to sigmoid. But as you move it, you can see that the distribution rather of points, the way that it compares when you look at the threshold as to where exactly the 0.5 line occurs, this threshold value occurs, you can see that as I reduce the quantile value here and reduce the value of tau, the requirement to reach 0.5 confidence score keeps decreasing. And as I increase the quantile, to reach this 0.5 value, I have to have a much higher input value. And so what we can use this for is to basically determine what the underlying quantiles of the latent function are. Using this empirical loss. And this is defined the exact same way that we would define binary cross entropy loss, except instead of using the distributions that we had earlier, they're using our integrated asymmetric Laplace density. You can look at the paper for further details about the exact derivation and the further steps. But what it really means, in essence, is that BQR allows us to capture the quantiles of the latent function. And in this example here, the image that you see on your screen, we have a neural network that was trained on some data points, and these data points were generated using a sine curve. The points in yellow are class 0, the points in gray are class 1. Our neural network knows nothing about the underlying distribution that we use to generate these points. All it knows is the x value and the corresponding class label. And yet, despite that, when we train, the network is actually able to decompress this information, and it's able to understand that yes, there is this sort of sinusoid function here, but along with the sinusoid, it's also able to capture to a certain degree the bounds of values that can exist at any given x. So if you see, for example, at x is equal to 0, if you were to draw a straight line down the middle, you would see that there are different possible class labels that can exist. And the quantiles that we generate allow us to capture all the possible labels that are there at any given point. And so before we get ahead, we need to first make sure whether or not these quantiles that we're generating are sound. And the best way we can do that is via something called coverage. So like I said earlier, mathematically speaking, the probability of a quantile being greater than the actual function is supposed to be equal to the tau parameter that was used to generate the quantile. So what we did was we took a couple of regression data sets. We took different threshold values, that's the T label that you see here, and we created classification data sets out of the regression data sets. And we used our quantile, we used the loss function that we described earlier to create some networks. We added a penalty term to prevent quantile crossing. And what we did was we computed this coverage value. We saw what percentage of points from the generated quantiles lie below the generated quantile and what percentage of points lie above the generated quantile. And what you expect to see is that the value should be close to tau in each case. And we found that for the most part, this is true. And it holds true for a variety of data sets under a variety of conditions as well. So in this case, we have both almost even class labels, so about 50-50 distribution with the first threshold value. And the second threshold value usually corresponds to a more imbalanced classification setting of close to about 80-20. In both cases, we see fairly good results, especially towards the center after we start looking at 0.2 to 0.8 quantile values. So what does this imply? Like, why does this even make any sense? Why is this a very interesting topic and why is it important? So the point is that now with BQR, we can capture the uncertainty in the latent, which means that at every x, we can now capture the possible range of values that f of x can have, which is in some ways a delta y. Or in some ways, it's exactly a delta y. And at every x, as a result, we can capture whether or not there are samples of opposite classes, right? Which is to say that is f tau of x above or below 0? And what that means is we're actually able to capture at any given point if our network thinks that there is even a likelihood that another class label can exist at this point. That is to say, I am on average predicting that at an input I'm saying that it's class 0, but there may be certain extremities which result in changing it to a class 1. And we can also find how far away from the median this class label can change, which means we're actually able to make a quantifiable metric that can be used to determine classification uncertainty. So that's what we call our confidence score delta as. Now, this is the formal definition, but in short, delta is basically how far away we need to move from the median for our class label to change. So take a look at the image that we have on the right. This is a heart disease function for an average patient. What we basically did was we trained a network on the heart disease dataset. We took 13 of the parameters, kept them constant, allowed one to vary. And this is just for visualization purposes. Nothing of that sort is required to actually use delta, but this is just to make it easier for people to understand. So what we've done now is we've got basically just one parameter that's allowed to vary, and we see how this latent function is changing. And like we said earlier, if the value is less than 0, it's class 0, otherwise it's class 1. Now, we decide to base our class label on the median, right? Because the median is the best representation of what the function is like. Not on average, but is the best representation of what the function is like. And at any point, we can sample how far away from the median we need to go to reach that class boundary, this dotted 0 line. So take this example here, right? At roughly 135 max heart rate. So we need to go from the 0.5 quantile to this red line, the 0.7 quantile, in order for the class label to change. And that means we have a delta value of 0.2 because we have 0.7 minus 0.5. If you look at this sample here at close to 160 max heart rate, we actually have to move down, right? Because our class label is already 1. So we need to go from this blue line here, this orange line here, which corresponds to a quantile score of 0.1. And this translates to a delta score of 0.4 because we have 0.5 minus 0.1. So why is this confidence score delta of any importance? Well, it's because if we know delta, we actually get a misclassification likelihood of any sample. Because if you think about it, the idea behind the median is that 50% of the points lie above it, 50% of the points lie below it. Now, if that's the case, delta actually tells us how far away we need to move to get to the function boundary. And we already know that 50% of the points from the median are towards the function boundary. And it means that 0.5 minus delta tells us the percentage of points that will lie on the opposite side of the function boundary. And that's why when we have a delta score, we have a misclassification rate of 0.5 minus delta for any point. And this is extremely, extremely powerful because what this means is that now when I give you a point, I can tell you not only how confident I am about whether or not it's right, but I can tell you what the likelihood of the misclassification actually is like. So what we did was we took a lot of different data sets and we computed the confidence scores and we grouped them together and looked at the misclassification likelihood of each group of those confidence scores. We took quantiles ranging from 0.1 to 0.9 for all of our experiments. And what we found was that there is exactly like what we expected. There's a very strong correlation between the misclassification likelihood and the delta score. So the lesser the delta score, the more the misclassification likelihood. And the R-square value, the goodness of fit between what we observed and our 0.5 minus delta was very, very high. We are close to basically 90% or 0.9 rather, for almost every data set that we used. And what this means is now when I look at a point, I can not only just say, okay, this is class 0 or class 1. I can look at the delta score and say, I want to trust my classifier's decision. I want to use this. And the great thing about this is now it actually gives us the ability to say we don't want to classify this point because we're too unsure about it. if you look at the function, the figure on the right, what we did was we took the p-medians data set, we trained it, we took the testing data, and we basically just computed the confidence scores and the class labels that we generated. And we grouped them together. And what we find is that the AUC ROC curve is very, very reflective of the delta score. So when your delta score is low, when your confidence score is just 0.1, the AUC ROC curve is very, very poor. You can see that the value is only just 0.54, the area under the curve, with 0.5 basically being the minimum that a curve should have, right? And as you go up the confidence score, this value keeps increasing, the area keeps increasing. Now, the catch here is that if I'm choosing not to classify a point, it's sort of an easy way out. So while we can measure the misclassification likelihood, we can also use this delta score to determine what's called a retention rate, which is to say what percentage of points have a confidence score greater than or equal to the delta score that I'm supplying. So if you take a look at the example on the left-hand side, you can see, for example, that in the ILP dataset, only 32% of points have a delta score of 0.5. And 87% of points have a delta score of 0.2 or greater. And you can use this as a way of determining how good your classifier is, because in short, it's a way of saying whether or not your classifier is able to capture its own uncertainties well, and how much label noise is actually present in the data that you're dealing with. BQR can be used for more than just, another thing that we did was we compared the delta score to something called the trust score, which is generated by Google. And we found that delta and trust score were again linked exactly like we expected. As the delta score went up, the trust score also increased. The great benefit that delta provides is that delta can be used in isolation. So all I need is the delta score for my one prediction, and I know the misclassification likelihood. The trust score is a relative metric. So the absolute value of the trust score is useless. You need to compare it with the trust score of all the other points that you have. Now, when we look at robustness as well, the standard rule of statistics is that the median is more resilient to outliers compared to the mean. And we see that in our data as well. When we classify using the mean, we get better results when we inject artificial label noise into our data. So you can see that on the right-hand side, where when we keep flipping the labels and introducing incorrect labels into our data, the degradation accuracy that we get from the median that we generate through BQR is less than the degradation that we experience with binary cross entropy. We also notice that the quote-unquote confidence produced by the probability score produced by binary cross entropy is usually more high than it should be compared to what BQR generates. So what we found was that BQR was more true to earth. It showed us scores of 80% when we expected to see 80%, while BCE was a bit more overconfident and gave us scores closer to 90%. And we can also use BQR to enhance explainability, because you can visualize your functions better. So like I had shown you earlier, what we have here is a very interesting graphical representation of a latent function. What we've done is we've taken this heart disease function that was learned by a model. We froze 13 parameters. We let the 14th one range from the minimum value to the maximum value in our data set. And we got, and what we did was we basically computed the quantile. We generated a neural network for this data set. We then froze 13 of the 14 different parameters and allowed the last parameter to vary. And so now we have these, we had 10 original quantile values that we could see. And these were rough, more jagged curves that we got from our network. And by using this smoothing function that you see on the right-hand side, using any kernel, we are actually able to get a smooth function representation, and we're able to interpolate quantiles. So we generated only 10 quantiles from our neural network, but we use this function to actually go beyond and generate quantiles that range from 0.05 to 0.95 in steps of 0.5. But previously we had 0.1 to 0.9 in steps of 0.1. And the great thing about this is that we can generate any quantity of interest by post-processing this smooth function that we generate here. You can apply the smooth function and the quantities that you generate with any standard off-the-shelf explanation techniques. So for in this example here, we have the Shapley values that we're computing. The Shapley values give us an idea of what variables are actually more important and more influential on the latent function. So instead of dealing with just class labels now, we're actually able to deal with the entirety of the latent function, which is a lot more potent. And we can also speed up BQR with something called the Lipschitz adaptive learning rates. In short, the Lipschitz constant basically tells how fast a function can change, and we can exploit this to speed up conversions. For the full details, please see all the references that are present in section 4 of the paper on exactly how LALR was defined. But in short, the Lipschitz constant of the PQR loss itself is the max of tau and 1 minus tau for every quantile. And what we found is, as expected, that we see a significant speed up in the number of iterations or the number of epochs that it takes in order for convergence to some fixed accuracy threshold. So we did all of our experiments on SGD, and you can see on the left hand side here we're dealing with smaller textual data and even the IMDb dataset, for example. We get a significant amount of speed up when we use LALR. We're actually getting an order of magnitude reduction in the number of epochs that we need to iterate through. On the right hand side, we have a performance comparison for image classification, because remember, BQR is applicable for any binary classification task. It does not depend on the nature of the data or anything of that nature. All it needs is for the class labels to be binary, and it works as an add-on to any additional network. So what we found in the case of the binary image classification was that we did see an increase in the number of, we did see a decrease in the number of epochs that were required. But for the Asira dataset, which is a large dataset and also includes colored images, we found that while we did see a reduction in the number of epochs for ResNet networks, the time for each epoch did increase. And for DenseNet, we also actually found that the number of epochs was on par or actually slightly higher than using a fixed learning rate. And a large part of this is because of the fact that we need to sample the penultimate output of the network. And so for larger networks, this becomes a more computationally intensive task, which is why the time per epoch increases. Nevertheless, we still do see significant benefits in most cases when using LALR. And so in short, when it comes to the limitations itself of PQR, the first big one is that it's only binary. We don't know yet how to extend BQR to multi-class settings. The first one is whether we can introduce a concept of something called depth quantiles, which is a new field of research. And the second is whether we can use something like a all-for-one technique to sort of create multiple classifiers for every class that we have, and incorporate BQR into all of those and use some kind of voting strategy to extend it forward. The second is how we can take this forward. So the first one is whether we can incorporate BQR into a training regime, because you have to keep in mind that f of x is the learned latent by the network. It's not the actual true distribution. So can we use BQR to punish overconfidence? Can we use BQR to get networks to learn faster when it starts straying away from the latent? That's one area. And the second is how can we combine something like adversarial attacks and BQR? Because adversarial attacks allow a measure of delta x. They tell us how much input needs to change in order for the output to change. And BQR allows us to tell us how much possible variation is present for the output given this input. Combining both of those together actually gives us both delta x and delta y, which means that we can actually somehow get an enhanced picture when it comes to the overall robustness of your model. So to conclude in one slide, Sigmoid and BC can't capture uncertainty in the latent learned by your neural network when doing binary classification. BQR can solve this by capturing the quantiles of this learned latent. By determining which quantile the label changes at, we can get an absolute measure of uncertainty or the likelihood of a wrong classification, which means we can accept or reject a decision based on our requirements. This delta score is one of the most powerful things that this paper is presenting. BQR is able to add on to any additional network that exists and at pretty much no additional computation overhead. It's just a matter of introducing n neurons for the n different quantiles that you want to generate. And you can use BQR to improve the robustness and interpretability of your models at next to no extra cost. The new research that's being done on adaptive learning rates with Lipschitz constants is directly applicable to speed things up. But unfortunately, BQR is only applicable right now for binary tasks. Thank you very much.